little discussion part here. So, I want to talk to you about a couple of concepts in chapter 19. Wait a minute, where did it go? Oh, yeah, that's right. I got to go like this, and like this. There we go. Now I got to hit the escape button. All right, so a couple of concepts in chapter 19. In particular, this diagram. This is a diagram that is in your textbook. And speaking of misconceptions, I think this is a diagram that can lead to some misconceptions. And what I've noticed with students when we talk about climate change, global warming, as a greenhouse effect, this visual pops into your head that I think sometimes is misinterpreted. And this type of a diagram can add to that misinterpretation. When you look at this diagram that is found in your textbook, it almost appears as though the atmosphere has a lid to it or a top. And if we think of the atmosphere like a greenhouse, very commonly students envision a roof or a ceiling that traps the heat in. And I don't want you to think of global warming in that way. Instead, what I would like you to understand are the specific gases that are involved in warming our atmosphere and just a little bit about the process that takes place to warm those gases. And so some of this we've talked about, and there's parts of this diagram that I think are okay. You can see the sun, and you can see this radiation that is coming from the sun. And then you see the radiation is kind of broken into three parts. Some of the radiation is reflected from the atmosphere and clouds, never reaching the surface of the earth. Some of the radiation does reach the surface of the earth. However, it is reflected at that time. And we talked about this concept of albedo, or a measure of the reflectivity of a surface. Now, we had some snow a couple days ago. And as you all know, because I've told you, and soon you'll know this, and because you'll be here in person, my classroom faces south, and the entire south window or wall is windows. And so my classroom faces the sun and the roof of that covers kind of the shop area of the new high school. And it's bright. So I've already closed all of my curtains. I hate to do it. It actually pains me. I love looking out the window, but the brightness is intense. Snow has an extremely high albedo, has a high reflectivity. And one of the things to notice in this diagram is that the diagram illustrates the solar radiation essentially passing right through the Earth's atmosphere. This is a concept that we have talked about, and I want to just stress this. The gases that are found in our atmosphere are largely invisible to solar radiation. The type of radiation, mostly shortwave, although the sun is such a large hot object, it emits radiation in every wavelength. But the shortwave radiation that is coming from the sun passes right through our atmosphere. Now, we mentioned in the past that ozone in the stratosphere is an exception to that rule. Ozone does absorb ultraviolet radiation, which is good because that causes various types of cancers in humans. But most of the radiation passes right through our atmosphere. Now, some of the radiation is actually absorbed by the Earth, and then that radiation heats the Earth. The Earth then re emits radiation, which you see in this red part of the diagram. And you'll notice that it looks a little different. Now, the part that I don't like is how it appears like that radiation kind of hits the top of this glass ceiling and then it bounces back. And so I've added to this slideshow a couple of other slides, which I think help illustrate what's actually happening here. So, and I like this one. So you have the incoming solar radiation, you have the heating of the Earth's surface, and then do you notice how this arrow represents a longer wavelength? Infrared radiation is found in a slightly different part of the electromagnetic spectrum. It's longer wave radiation. And just so happens that there are gases in our atmosphere that are really good at absorbing that particular wavelength. And so instead of 100% of that radiation escaping Earth, escaping the atmosphere, and essentially being radiated to space, it is absorbed by CH4, which is methane, water in the vapor form, and carbon dioxide. Those molecules in turn heat up and they re-emit their own radiation, which we feel as heat in our atmosphere. And so I like this diagram because it gives you a much better visual of what is actually happening and the interaction of that long wave radiation from the earth, not the sun. That's the big misconception, is that our atmosphere is heated by the sun. The sun heats the earth, which in turn heats the gases in the atmosphere. And so I want to consider these gases now for a moment. And you should recognize these gases as greenhouse, global warming, climate change gases. Okay. Water vapor, carbon dioxide, and methane get the most attention. Nitrous oxide, tropospheric ozone. This is not ozone in the stratosphere. This is ozone that is produced near the surface of the earth. A little bit different process going on there. We talk about this a lot in chapter 15. Chapter 15 covers air pollution and specifically ozone. But these are the ones that get the most attention. And it's important to be able to distinguish a couple of characteristics of each of these gases. So first of all, carbon dioxide gets a lot of attention. Okay. And the reason carbon dioxide gets a lot of attention is because carbon dioxide is the gas that humans contribute to the atmosphere in large quantities when we burn fossil fuels. And so coal, natural gas, and oil are fossil fuels. Those are carbon-based fuels. And when you burn a carbon-based fuel, the combustion reaction releases carbon dioxide. And so what we have observed since the Industrial Revolution is this number right here increasing. And we know in the year 2021, the concentration of carbon dioxide in the atmosphere is over 400 parts per million, probably somewhere closer to 410 parts per million. And so I want to focus on this little concept of global warming potential, though. So when we talk about global warming potential, what we're talking about is a specific gas's ability to absorb that radiation that is coming from the earth. And so if we think of carbon dioxide as being a unit of one, then we have a way to compare carbon dioxide to other gases. And so methane is a gas that has received attention lately, not because the concentration is as high as carbon dioxide, but because methane has a much, much higher global warming potential. So you'll see this number 25 here, and that number 25 means that a molecule of methane has the potential to absorb the radiation coming from the earth at a rate of 25 times greater than carbon dioxide. So even though methane is found in much smaller concentrations, a smaller concentration of methane does have the potential to increase the temperature of the atmosphere. And so when we talk about methane in places like Siberia, where climate scientists worry that as the permafrost in Siberia melts and methane is released, those concentrations of methane could contribute to a warmer planet. I want to draw your attention to chlorofluorocarbons. And again, chlorofluorocarbons, or CFCs, have a much, much greater global warming potential than methane or carbon dioxide, thousands of times higher. But chlorofluorocarbons have largely been eliminated from production on planet Earth. It turns out in the 70s and 80s, when chlorofluorocarbons became popular as an industrial product, turns out we discovered that they interacted with ozone to create a new compound and essentially destroy ozone in the stratosphere. If we do not have ozone in the stratosphere, then we are susceptible potentially to ultraviolet radiation and all the damage to our skin and cells that comes with that. And so chlorofluorocarbons were actually eliminated, and we're going to see again in chapter 15 a lot of information about CFCs. But what replaced them in industrial use were hydrofluorocarbons, which do not destroy the ozone. However, they do still have a very high global warming potential. And so refrigeration is an area that is not talked about much when it comes to global warming, but it actually can play a really important role. And as it turns out, if we look at that ideal gas law, if you think back to our discussion of convection currents in the atmosphere, we talked about this concept of PV equals nRT and the relationship between pressure of a gas and the temperature of a gas. And if you compress a gas, the volume of gas or that gas body heats up. And so if you want to use that physical law to create refrigeration, you can. What you do is you have a compressor, and your compressor takes a volume of gas and compresses it. As it compresses that gas, one of the byproducts is heat. So you vent that heat to the outside somewhere. And then you pass that gas through a little pipe and you allow it to expand into a chamber that is adjacent. As that gas expands, it cools, and now you have refrigeration. Okay. And then you just continue to recycle that process. Take the gas, put it back into the compressor, squeeze it. You have to vent the heat out. And then as it expands, you take that cold air or the coldness of that, and you can use that in refrigeration. And so this process takes place at home in your refrigerator. It takes place in your air conditioning unit. And then in large scale, think of all the large scale industrial applications of refrigeration, even going to a local grocery store. The deli section of a grocery store has large scale refrigeration display cases. Usually there's three or four different rows or aisles of frozen food. And slowly those gases can leak, and then those gases can contribute to global warming. So those fluorocarbons are small in quantity, but really high global warming potential. This is something that you should remember. Okay, you should remember what the greenhouse gases are, and you should have a pretty good sense of their global warming potential. Okay, so Ms. Eno asked you about this concept of raw materials used to make this biomass, and science teachers, we're really guilty, I think, for creating this misconception. Um, where does the tree get the raw materials to build the biomass, to build the trunk and the leaves and the branches and the root system? The raw material comes from the air. And for students, a very common answer is the soil. And trees are solid, soil is solid, and there's where that connection is made. But the answer is actually the air. And when we think of photosynthesis, very commonly students will think of photosynthesis as the energy source for plants. And that is absolutely true. But a better way to think of photosynthesis is really a plant creating a carbohydrate. Um, the plant takes water and carbon dioxide in the presence of sunlight, and the plant creates glucose, creates sugar, carbohydrates, C6H12O6. That glucose molecule can then be broken down during respiration, releasing energy that the plant or the animal can use for everyday activities. Or that glucose molecule can be linked together to form biomass. And this is an important concept because when we talk about carbon dioxide as a global warming gas, commonly we will talk about two things related to that. We'll talk about the human sources of carbon dioxide, burning fossil fuels, and fossil fuels originate from plant material, and the carbon in that plant material originates from photosynthesis. So when we examine coal, oil, and natural gas, we're really examining a byproduct of photosynthesis. The second thing that you hear commonly is this idea that trees can be used to combat global warming by taking carbon dioxide out of the atmosphere. And so, if you hang on to that misconception of plant biomass related to soil, then that's not something that is easily understood. So the carbon dioxide that the plants are taking out of the atmosphere can be used to actually build the plant itself. And if you look at an oak tree, a mature oak tree in and around Verona, those oak trees weigh thousands and thousands of pounds. It represents thousands of pounds of carbon dioxide. So a better way to think of photosynthesis is really as a producer of glucose. And one of the things that I do find sort of interesting about this, if you think back to our detention pond project and our detention pond discussion, one of the things that we talked about was this idea that the first stage of our detention pond to handle our stormwater includes an infiltration field. And so one of our goals is to keep as much of that stormwater here on site as possible, rather than sending that stormwater downriver to the Sugar River and ultimately to the Gulf of Mexico. Let's just absorb it back into the ground right here in on our campus. And what we use for that are native prairie and native wetland plants, some of which have a root system that can be 5 or 6 feet deep. Well, if you think of a plant like that, a herbaceous plant, prairie plant in particular, that has a deep root system like that, what that plant is doing is photosynthesizing, making those glucose molecules, but then taking that carbon based glucose molecule and using it to build a root system that is, in some cases, 6 feet in the ground. So when that plant eventually dies, that carbon is still in the ground. And so, in terms of actually taking carbon out of the atmosphere and sort of packing it away somewhere, in some ways, it actually makes more sense to encourage the growth of plants that really do store the carbon under the ground. This tree in our lifetime is going to remove carbon dioxide from the atmosphere. But eventually, this tree is going to die. The majority of the biomass or carbon in this tree is above the ground. It falls to the ground. Bacteria begin to eat it. The bacteria eventually respire and they spit out carbon dioxide, which returns it to the atmosphere. So in our lifetime, trees are good at pulling carbon dioxide out. But in terms of actually long-term storing carbon, there's an argument that deep-rooted herbaceous plants actually might do a better job. Coal, natural gas, and oil is just a byproduct of that photosynthesis. If you have plants that grow for many years in areas where decomposition is slow, you need an area where decomposition does not take place rapidly. And if you examine, for example, the leaves that fell in Stewart's Woods, our new school forest is called Stewart's Woods. If we go out to Stewart's Woods in the springtime, you're going to see in that old layer of the soil, that top layer, the organic layer, a thick cover of leaves. By the middle of summer, July, August, a good chunk of those leaves are going to be gone. They will have been consumed by any kind of invertebrate that's in the soil, bacteria, decomposition. And by the beginning of fall, before the next year's worth of leaves fall, almost all those leaves are completely gone. Well, in a swampier area, the vegetation that falls in the swamp, decomposition is slowed because those aerobic bacteria are not present in sufficient amounts to decompose all the plant material. So the plant material begins to build up. If later then that plant material is covered by an ocean or by sediment, rocks, if you compress that plant material for a couple 100 million years, 100 million years, you can end up with a fossil fuel like coal. The thing that's important to remember when you have a fossil fuel like that, that fossil fuel is not part of the current carbon cycle. That fossil fuel is locked away. And so when we consider this cycling of carbon through the atmosphere, oceans, etc., what we have humans have done, what we have done is we've taken that carbon that's under the ground and we keep pouring it into the cycle. We're adding it to the cycle. And that is what is driving global warming to a large extent today. That's where that extra carbon is coming from. Okay, I'm going